Okay, so I will start then. So regarding your chessboard, I know that I keep asking you the same question. Can you quickly explain why we could not homogenize such a space-time chessboard? Why it's forbidden to homogenize it?
Okay, so let me, okay, well, it depends on which checkerboard you mean. So if I'm looking at
such as this one.
Okay, yeah. So for this one, so if you want to homogenize it, you can, because the okay. So generally speaking, you can apply homogenization only in certain scenarios. Even like in the case of a space-time laminate, you can do that only in a certain regime. That is when the homogenization is going to work. Here, it's very similar. You know already what the effective velocity, the speed of the wave is going to be, because the two materials have the same speed. For what concerns the, so here you would probably want to find what the effective impedance is, but so for, okay, let me find to okay, so here, just for these two very special cases, you may find what the effective wave impedance is, but only for those two cases, because for those two, the condition of PT-symmetry is always unbroken. So here you could find it. But if you want to go to any other design, like these ones, for which you don't have that the condition of PT-symmetry is always satisfied, you're not going to be able to find it. Even in the case where the condition of PT-symmetry is unbroken. So the main thing comes out of the fact that these materials behave more similarly to time laminates rather than, okay, so probably let me say this. So you have space laminates, time laminates, and everything in between that is basically represented by these geometries. And there is like a sort of threshold in between where you can, there is a window in these two extreme points where you cannot apply homogenization. But then for any structure that is closer to a space laminate or that is closer to a time laminate, you can do that. That's kind of like the idea. So a structure of this type would follow in the window where you can apply homogenization. Whereas a structure of this type will follow into the previous window where you can apply homogenization. Yeah.
And I've got another question, and you know, maybe it's another tricky question. What happens now if you add up some anisotropy, you know, inside of these black and white squares? So can you add some kind of anisotropy inside of this chessboard?
Yes, but then you have to change the geometry in the sense that, so here I have a, okay, sorry, let me go to this one. So here, for instance, you have a geometry that is symmetric in X and Y, because we're assuming that the properties are the same in the X and Y direction. If they're not, then you have to change that. So the geometry in the X direction will be different than the geometry in the Y direction, for sure. But so depending on how they are different, you need to come up with a geometry so that that design principle is still satisfied, so that each wavefront and all the scattered waves will go from a time interface to a space interface. If you manage to find a geometry that does that, then you're on board. Then you will have a constant amplitude of the wave as it travels through the material. So that is what you need to do. You need to modify the geometry in X and Y in two different ways. So theoretically, yes, you can add anisotropy. I haven't done that, but it's a very good point.
And regarding this wonderful experiment of Fink's group, how does it relate to your equation? So
Yeah, it's very different because what they do is they have, so, well, it's not too different, but so the way that let me go back and show like an equation. So the way that I consider time modulation for me is by changing the parameters in the wave equation. The way they do it is by changing the, they have a source in this equation, so it's not a homogeneous one. They have a term that takes into account gravity, and that's what they change. So it's different in that sense. We are working with different equations. And then in their case, given that they're working with water waves, they do not simply have a second order linear equation of this type, but they have some additional terms that are strictly related to a wave propagation in waves. Yeah. But the main difference is in the source term that they don't have in my equation.
Super. I think we have a question from Professor Fernando Fraternali.
Yeah. Ciao, Ornella. Hi, Ornella. Nice to see you again. So I would like to understand a bit more in detail what do you mean with a space-time microstructure, especially in time. What do you mean with this term, space-time microstructure?
Okay, yeah, sure. So, okay. So in this example where I have a time laminate, what I do is I start with a homogeneous material. And then at a certain moment of time, I change the properties of the material into something else. So from alpha 1, beta 1, I end up with alpha 2, beta 2. And I do that for the whole material. So here there is no space geometry whatsoever. This is just a change of the properties in time from a homogeneous material to another homogeneous material. When I say space-time microstructure, it means that I start with something that already has some spatial interfaces in there. So I start with something that already has a geometry in space. In this case, you just have, for instance, a space laminate. So you have material 1, material 2, material 1, material 2 that are layered in a one-dimensional element. So this is the space geometry at time t equals 0. Then what I do is at a specific moment of time, I flip the materials by changing the external field. So that 1 becomes 2, 2 becomes 1. So this will create the time geometry on top of the space geometry that you already have. So what you end up with is this is space-time shapable, where you have material 1, material 2, material 1, material 2 in the x direction. And as you do the time modulation, you go from 2 to 1, 1 to 2, 2 to 1 in the t direction.
Okay. So instead of an evolution, yeah.
Go ahead.
So you look at an evolution problem as a change of microstructure. So is you give a geometry to the change of microstructure in time, kind of geometric description of the change of microstructure in time.
Yes. So that's my design principle. I say how you have to apply. So the beginning has, so for instance, in this more general scenario, here you start again with elements of material 1, material 2, material 1, material 2. Then at this moment of time, everything changes into the Y material. And then at this moment of time here, only these segments here change into material 3. Then at this moment of time, everything goes into material 1 and so on. That's like the, that's how it works. So yeah, I'm prescribing how to apply the time modulation that has to be commensurate to the space geometry that you have in order for these field patterns to take place. So that's my design principle.
Okay, nice. Thank you.
Thank you.
Super. Do we have any more questions? Okay, in the meantime, I've got the obvious question. What happens if now you have, some rank 4 tensor in your equation? So you're moving from acoustics or electromagnetics to in-plane elasticity, let's say.
Well, when you work with, yes. Okay, so so if you work with, there are already some results. For instance, in the one-dimensional case by Constantin Lurie, for the case of shear waves coupled with longitudinal waves. So the way that they treat the problem is by assuming that the wave impedances are equal to each other. That will ensure that the say the longitudinal waves will not have any reflected wave, but you will have them for the shear waves. And so they look at the coupling between the two when you have space-time modulation. I haven't looked into that, but there is already some work out there.
Okay, it's good to know. And again, going back to the water wave problem, again, well, in the case of the water wave problem, so there are some experiments, and I mean, can you think of turning Matthias Fink's experiment into your, chessboard problem? What would you do, to map the Fink's experiment onto your let's say water wave space-time chessboard? What would you do?
Well, I would, okay, so first of all, I would just, okay, so in that example, they have the same wave impedance. What changes is the wave speed. Yeah, I'll have to try to come up with a space-time microstructure so that the wave impedances are the same, the wave speeds are not, but I know how to change them and see how the characteristic lines associated with that equation will combine in order to achieve the same result. So yeah, I would have to, you change equation, so the characteristic lines will be different, but yes, I would just have to basically apply the same theory to that case.
And these lines would be called caustics. How would I mean, at the surface, the free liquid surface, you would see some kind of caustics. I mean, what would you observe?
Yeah, so I have to think a little bit about it. Yeah.
I mean, ideally, what you would like to see is pretty much what you draw with your red segments, yes. No?
Yes, yes, yes. Yeah, that's exactly right. I have to think a little bit about how the characteristics would look like for that case. This shouldn't change too much, but I haven't looked into it. So that's a very good suggestion. Yeah.
I mean, it's really fascinating. Okay, so any more questions, people? Please feel free to ask any question you have in mind. It's a unique opportunity to talk to Ornella, who is really an expert of this chessboard metamaterials.
So, Ornella, if I may ask a second question.
Go ahead.
Ornella, so can be related to 4D printing? 4D printing, can this be related to 4D printing? So this technique of 3D printing with changing in time, so as a tool for creating these materials, these applications.
That's a very good question. So okay, so yes, it could be. So I'm just thinking, so here the key thing is that you have to be able to change the material properties instantaneously in time. So I know that it's possible to realize 3D printed materials, for instance, that are made of piezoelectric materials, so that you can achieve that instantaneous change of the material properties. I don't know how you would do that.
Also with magnetic fields, maybe magnetic fields will change physical properties.
Yes, so technically, yes. I'm not an experimentalist, so I don't know at the top of my head, like how one could do it, but for sure. And yes, so as long as here the difficult part is to understand how to realize the time modulation in a way that it's you have these instantaneous changes. Once you figure that out, then yes, you can use.
You can, yeah. Okay. Okay.
Yeah. Yeah. So all the examples that I saw in the literature where time modulation is applied in this sharp way, where you have these time interfaces, they use, as I showed earlier in my very first slide, they use, for instance, for mechanical waves, so you have a piezoelectric patches, or in the here.
Mm-hmm.
Yeah, that's what you have. Or in the in electromagnetic waves. By the way, this experiment was realized like a couple of months ago, because it's very, very complicated to realize perfect time interfaces in the context of electromagnetic waves. So I think that the complication really arises from the difficulty of making sharp time interfaces in real life. Yes.
Okay.
But it looks like we're getting there. So
Yes.
So regarding this slide, what would be the frequencies in question? Because if it's electromagnetic waves, you know, the spectrum is really large. So are we speaking here of
microwaves here? So here the spacing is chosen so that they work in the microwave regime. Yeah.
And actually, I think that the group of Riccardo Sapienza in Imperial has also achieved, and this is quite amazing, some space-time modulation in the terahertz range.
Oh,
so, yeah, and these are experiments. So I think they have experiments on space-time metamaterials in.
Oh, I'll look into it. Thank you for the reference. You know, this field is changing so fast.
Yeah, I mean, it's amazing. I think it's totally amazing because, you know, just a few years ago, people would think it was just fantasy. I mean, just great for theory and numerics, but now I think it's reality, you know, and not only for acoustic and elastic waves, but yeah, I mean, we are beyond microwaves. I think it's really now optics, photonics, which is well, fourth dimension, you know. We need to count with time. Yeah, I mean, this is really exciting what you've been doing. I'm just amazed by all your ideas, and I really hope that you know, some kind of water wave experiment can be built. I mean, I'm sure some water wave experiment can be built for what you are proposing.
I mean, yes, as you said, what I have to do is to just to see whether these microstructures will work also for a different type of wave equation. That's all I have to do on my end. Yes.
So there is this Mills-Slope equation in water waves, and the good thing with the Mills-Slope equation, so when you have a variation of the you know, depth, it has two parameters. So you can really map your equation on the Mills-Slope equation. Maybe we could chat a bit about, yes. So because usually in water wave theory, you are stuck with a single varying parameter, but here, you know, it's a change in bathymetry, and so you have two parameters, and perhaps this maps very nicely onto your theory. Perhaps.
Yeah, no, thank you for the suggestion. Now we'll look into it for sure.
Yeah, so with that, I would like to thank you again for this inspirational talk. And thank you very much, everyone, for attending Ornella's talk. And I hope to see you next week again for our webinar series. Stay safe. Bye-bye.
Thank you very much,
Bye.
everybody. Bye-bye.
Bye.
Bye. Bye.